great folks. It's a technical lecture about how to solve simple differential equations. We will start with the classification and some of the equations that you've already seen, either in Chem 1047 or in the chemical kinetics courses. And then we will proceed to solve equations that we have not yet seen. In particular, in the context of chemical kinetics again, we will be looking at systems that are not autonomous, but systems to which chemicals are continuously added or continuously removed from them. But first things first, classification. So a differential equation is an equation that involves not numbers but functions. You have to look for a function, and it involves its derivatives. They are classified very broadly into ordinary differential equations, where the derivative is with respect to just one variable, and in most cases in chemistry that one variable would be time. But I've given you an example from electrodynamics, so d2 by dt squared of a current in an electrical circuit plus 1 over the capacitance and the inductance of the two elements of that circuit, I of t equals 0. And this differential equation refers to a circuit like this. If that's a capacitor of capacitance C and that's an inductor of inductance L, even though there are technically speaking no sources of current in this system, there are no batteries and so on, but if you recharge this capacitor and let the system go, capacitor will discharge itself through the inductor, magnetic field will appear, and as the capacitor is fully discharged, that disappearing magnetic field will drive further current, and so this circuit actually displays an oscillatory current. It goes as a sine or a cosine, and that's the equation that describes it. As you can see, second derivative of a sine or a cosine is again a sine or a cosine, and if that cancels, you get 0. So this ordinary differential equation describes the current dynamics in a simple circuit. And then they can be partial. And this is for the cases when there are multiple coordinates that system depends on, and we have partial derivatives with respect to those coordinates. A good example is diffusion equation, where the concentration of the substance would depend not only on time, but also on the location within your sample. And partial differential equations are way more complicated. So for example, with the diffusion equation, d by dt of the concentration, that's the function of spatial coordinate vector and time. It will be the diffusion coefficient d, and then d2 by dx squared plus d2 by dy squared plus d2 by dz squared, acting on c of r and t. So the way to read it is we have to take our function, take second first derivative, second x derivative, second y derivative, second z derivative, add them all together. As you can imagine, finding a function that would satisfy a monstrosity like this is a non-trivial exercise, and you'd be pleased to know that the equations describing the hydrogen atom are even more complicated. And so when we will get to atomic orbitals and so on, we will actually be solving the full Schrödinger equation for the hydrogen atom. I can promise you a few boards densely filled with some pretty horrible algebra. So these are actually relatively straightforward cases, and when you go into things that modern computational chemistry is dealing with, it is becoming a royal blast, at least so far as analytical treatments are concerned, and so people overwhelmingly prefer to do them numerically. Okay, so we will get to partial equations after Easter, if memory serves. And for now, we're dealing with the ordinary ones, particularly the more complicated types that you have not yet seen in your chemical kinetics courses. So, further classification of the ordinary ones. The principal difference that we will come across in this course is between linear and non-linear differential equations. So a linear equation is the one of the following form. Pn of x, f nth derivative of x plus p n minus 1 of x, f n minus first derivative of x, and so on, all the way to p1 of x prime of x, so just first derivative, plus p0 of x f of x, so the zeros derivative, all equal to some g of x. Looks pretty horrible, but really the important thing in here is that the unknown function and all of its derivatives must enter linearly. So that is a linear term with respect to n's derivative. This is linear with respect to n minus first derivative. This is linear with respect to f of x. So you cannot have a square of a derivative or a cosine of a function that would be nonlinear. And those equations in general actually don't have any solutions or are ridiculously hard to solve. But essentially the equation that has this form, where Pn can be anything, just arbitrary functions, so long as all the derivatives enter linearly, this is called a linear ODE. Then the second step in the classification refers to this g of x. If we rewrite this as a function not of x but of time, this would be closer related to chemical kinetics. In that case, this g of x will be the time-dependent quantity of the substance that we are adding or removing from the system. So the equation for which g of x is equal to 0 is called homogeneous. And when it is not equal to 0, it's called inhomogeneous. G of x 0, and you have seen examples of homogeneous equations already, for example, radioactive decay or other chemical kinetics, but we will look today at how to solve the inhomogeneous equations. Okay, so that's for the linear ones. Then, if you look at more of a physical meaning of what goes on in here, you can have an equation of motion with respect to time of the following form. Say f nth derivative of time will be some function of all the other derivatives. F of time, f prime of time, and so on, f n minus 1 of time. If it is possible to write the equation in this form, it is called autonomous. And perhaps the best illustration for what this means comes from chemical kinetics. If I write some simple second order kinetics, say dA by t will be minus ka squared. Imagine that we are starting to add or remove substance from here. So we add some source. So concentration as a function of time is just a simple second order process. Put this now, something simple, dimerization. And then there's a student standing there with a shovel and just adding something into the system. Such a system would not be autonomous because student is present and is doing something to it. So from the physical perspective, the system is not left on its own. So it is not autonomous. However, if we remove the student from the system, it will start evolving like that. Just the standard chemical kinetics. And now the system has been left to its own. There are no external influences, and such a differential equation is called autonomous. As you can imagine, non-autonomous equations are harder to solve because generally S of t could be any homogeneous schedule by which you are adding reagents. Another type of classification for differential equations is by order. So the order is simply the order of the highest derivative that you see in it. Overwhelmingly, so far, except in this course, you have only seen first-order differential equations, because chemical kinetics is necessarily first-order because you are basically dealing with reaction rate. Reaction rate is deconcentration by dt, it's the first derivative, and so you've only been dealing with first-order ODEs so far. But there are plenty of second-order ones that are important in physics. For example, d2 f of t by dt squared, as I've already shown you there, when it's minus squared f of t. It's an oscillatory process. This is called the wave equation. Particularly when it has some spatial coordinates, it describes oscillatory motions. In engineering, there are even higher order equations when you are considering mechanical deformations of engineering structures. You get fourth order equations, d4 f of x by dx to the power 4 equals something really complicated. I will not actually go deeper into what it is. But this is Euler-Bernoulli equation for the deflection of a beam. So if you have a bent structure, it obeys a fourth order differential equation. So, deflection. Now, excuse me, the classification that is relevant to us, because we will be solving such equations, is first order ODEs are classified into separable and inseparable. So if we have a homogeneous first order, things like that, df by dx equals some g of f and x, or equivalently y by dx is some function g of y and x. It is sometimes possible to rewrite these equations in the following form. You have some function, let's call them a of x dx equals b of y dy. So essentially you collect all x variable on one side of the equation and all y variable on the other side. Such equations are particularly easy to solve because you can simply integrate both sides and then you're done. And you've seen them before, they're called separable. Equations for which such procedure is impossible, at least from their immediate appearance, are called inseparable or inseparable, I think. Okay, so this is the classification. What we will be typically dealing with up to about ISTA are firstly ordinary differential equations. Secondly, mostly linear ones with an occasional non-linearity when we have to deal with things that are chemically relevant. We will be looking almost exclusively at first order differential equations, so none of this complication. And then we will be looking variously at separable and inseparable, homogeneous and inhomogeneous equations. Okay, so let's go into practicalities. Let me just quickly run through an example of a solution that either I or chemists have already told you about, and those are simple things. So, example of a separable linear first order case. So say dy by dt is x plus 10 sine x. And we would like to have a solution for this for which y of 0 is 1. That's the differential equation. This is called the initial condition. If we had it not at 0 but somewhere else, that would have been called the boundary condition. And as all of you know, this is almost trivially easy to solve. So we have dy equals, we can move the x over to the right hand side, so it's x plus 10 sin x dx. We moved it into the separated form. This is immediately integrable. So we would have here y plus a constant equals x squared over 2 minus 10 cosine x plus a constant. Constant plus or minus a constant is another constant, so we don't need this here. And this is our y of x. A solution of this type that satisfies the differential equation and has undetermined constants is called the general solution. The solution that we obtain by actually substituting in the additional information from here is called a specific solution or particular solution. So if we say, okay, y of 0 must be equal 0 over 2 is 0, 10 cosine 0 is 1, so minus 10 plus c must be 1. Therefore what we have in here is c equals 9, no, 11. When we put it into that solution, it's called the particular solution. And up to here, you have seen this many times from radioactive decay, from second order kinetics, from the 1047 module. So all of you, in one way or another, have already been exposed to solving these things, and you'll get a little bit of extra practice in the workshop. What you have not been exposed to, however, is the solutions of the inhomogeneous equations, and this is where it gets interesting. So let's go back into chemistry and consider an example where a chemical reaction proceeds, but in a situation when we are adding or removing substance from the reactor at a constant rate. So the interesting part for today is the general form of an inhomogeneous equation follows from the definition here. So if we look at the first order one, the general form will be something like f prime of x equals plus a of x f of x equals some v of x. When we looked at this previously, right, so that equation over there, the difference was that this term v of x wasn't present, or we could actually get rid of it by the variable separation procedure by just integrating it here. This is not in general the case, and so we will be seeing equations of this type where a procedure like that is impossible. So the way to solve this is as follows. First, we write down the equation as if this v of x did not exist. So solve the homogeneous version. So we rewrite this equation in terms of a different function, but for b equals to 0. So let's say g prime of x is plus a of x, g of x equals 0. This is exactly the same equation, but we replaced function f with the function g because of course the solutions will be generally different, and we have forgotten about b. Such things are easy to solve by the variable separation procedure, because this is dg by dx plus a of x, g of x equals 0. What I can do is I can move this over to the right hand side, divide by g, multiply by dx, and so what will happen is dg over g like that equals a of x dx. this is instantly integrable, and so we get the solution. But of course, we get the solution for the wrong thing. It is not the solution to the original equation. So, basically here obtain g of x. The second step here that I will give to you without proof, the proof exists, but we unfortunately do not have sufficient time in this course to fully do it, is we look to the solution of the following form. F of x is some unknown function, c of x, times the function we have obtained in the first step. You can probably see how this makes sense. Imagine that we are looking for a solution of this. If this were true, right, that G is the solution to the inhomogeneous one, and this is some other function, what would happen is when we substitute it over there, the product rule in the derivative will get c prime of x times g plus c of x times g prime. Part of that equation will be satisfied and two terms will appear. We can try and make the first term cancel this one and the second term to match b of x. So it does not appear all too implausible from what we know about the properties of a derivative that such a solution might exist. So this is a hand-waving argument to it, and of course the proof of the pudding is if we actually manage to obtain a solution like that, and that would be it. But there's a generic proof for this, which I will just ask you to take my word for it, that this is always possible, at least for the linear, non-homogeneous differential equations like that. Okay, and so we substitute that back, so subst into original equation. And then find c of x. As soon as we know c of x, we can assemble the final solution. And because this is a fairly protracted procedure, the essential step C, of course, is check. Take your final answer, put it back into your original differential equation, and make it absolutely certain that the original equation is satisfied. So, that is the general map of what we are going to do. And now let's go into chemistry and solve that particular equation with a source term in it by following that procedure here, and there will be more of those in your workshop. Just some space in there. Okay, so first order chemical kinetics. dA of t by dt minus Ka of t, with the difference that there's an extra constant in here plus K2. So the substance is reacting at the rate K1, but also it is being added into the system at a constant rate K2. And this K2 is our P of x, in that it creates this inhomogeneity in the equation. Variable separation is no longer possible, because if you divide this by A of t, it will of course appear here, but it will also appear in the denominator of K2, and so you can no longer separate this. Okay, let us solve the homogeneous version. So we will have another equation, A homogeneous Let's use the same variable g as we were using in here. So our dg by dt is minus k1 g of t. So in here we have a time-dependent process. This plan is formulated for the independent variable x, but I'd imagine you're all sufficiently grown up to be able to substitute x for t and for an independent process for a time-dependent process. So this is our homogeneous differential equation, for which, of course, we know the answer straight away because we have solved this many times. This is linear first-order kinetics. Our g of t is some constant e minus k1 t. I trust that nobody needs me to reproduce the integral and the logarithm and then the exponentiation again, because I've probably been doing it ad nauseam by now. This is our step A, and we have solved the homogeneous equation. Therefore, now in the step B, we will be looking at finding the A of t, and our A of t, as per the instructions over there, will be some unknown function times this. Well, we can absorb the coefficient into the unknown function. So if there has to be a function in here, why don't we just package the coefficient into it? And so we will be looking for some function c of x times e minus k1 t. Sorry, c of t. Where c of t is unknown. And we will find it now by substituting this so-called ansatz into that equation. So this is our ansatz for this product. It was x there, it is t there, but that's just the independent variables, it has a different name. Putting it in there, we have c of t e minus k1 t prime, it's dA by dt, is equal to minus k1 c of t e minus k1t plus k2. Notice now that this is an ordinary differential equation, but this time it's a differential equation for the function c. Let's open that up using the product rule. C prime of t e minus k1t minus c of t k1 e minus k1t equals minus k1 c of t e minus k1t plus k2. Notice that immediately something cancels. And this is kind of diagnostic. If you are substituting that ansatz in, and that immediately cancels with this, or something else immediately cancels with something else, then you are doing everything right. If it doesn't cancel, or worse, it adds up, check your arithmetic. At the second stage of this homogeneous solution, something must always cancel, because such is the nature of that solution, right? We have a function here that partially satisfies the equation. So a lot must disappear, and only the things that are directly relevant to the source term must actually remain in there. Okay, so that goes, and that goes. We have a much simpler equation in the end. So we have c prime of t equals k2 e k1t. So I have moved this exponential over to the right-hand side. And this is, of course, trivial to integrate. We just integrate it immediately. Let's see if I haven't made any arithmetical mistakes so far. No, I haven't. Okay, so that's a c prime. So that's the dc by dt. dc by dt is k2 e k1t. Variable separation, so move the dt over to the right-hand side. dc equals k2 e k1t. Integrate both sides, and therefore our c of t is K2 over K1 E K1T plus a constant. Let's call it something else. Let's call it T. It's an indeterminate constant of integration. So far, so good. So we have obtained our T, and of course, the final thing is to assemble the final solution, which we have here. This exponential there, and we have now found that unknown function. So let's clean up some more space and continue functions and mathematics. That's our C, and so A of T is now going to be K2 over K1 E plus K1T, so that one is a plus our indeterminate constant E minus K1T. We can open the brackets, and a few things will cancel themselves out. A of T will be K2 over K1. That times that cancels, plus D E minus T. And this is our final answer, and let us now analyze it a little bit. It still has an undetermined coefficient, so this is a general solution to that inhomogeneous equation. Two things that we now need to do is, firstly, we must check whether it actually satisfies the equation that we have, which is not obvious if you look at it. And secondly, we must look at various cases where we do know the initial concentration to try and find out what this D coefficient is. So item C on the agenda, as per the plan here, is to substitute and check. So dA by dt on the left-hand side there, these two constants disappear in the differentiation. That gets differentiated, so minus d k1 e minus k1t. That's the derivative dA by dt. Must be equal to minus k1, that solution, minus k1 k2 over k1 plus d minus k1t plus k2. Let's see. K1 will cancel. We are left with minus k2, which will cancel with this. Minus k1 de minus k1t minus k1 de minus k1t. The left-hand side is equal to the right-hand side, so very good. What about the particular solution? Well, for that we would need to pick some initial condition. Let us pick a situation where there was nothing in the reactor at time 0. So not only did the reaction not start, but the reactor was actually empty. So we will pick up the condition where A at time 0 was 0. And then, of course, what starts happening is the substance begins to arrive into the reactor at rate K2, and as soon as something in the reactor, it starts being consumed according to the first order process. So, as you can see, mathematics here is dealing virtually automatically, right? You are not making any special effort towards that, with a fairly complicated combined process. Something is arriving, something is being transformed. We can add further differential equations as to what it's actually transformed into, and it's transformed backwards. And you can easily see how you will develop a picture of an entire chemical process, perhaps in some complicated facility, with multiple reactors transferring between those reactors and so on, all by just sitting and fiddling with a pencil, or in the more convenient case, a computer. Okay, let us say that is true, so what we must have is K2 over K1 plus D E minus K1 times 0 must be equal to 0. Well, the exponential of a 0 is 1, and so that disappears, and of course this simply means minus K2 over K1. And so the particular solution in our case will be as follows. We will have A of t will be, D can be taken out of the bracket, so K2 over K1, 1 minus E minus K1 t. So if D is the negative of that, then we can take it out of the bracket. Here it is, 1 minus E minus K1 t. Let us now analyze this solution and see where it goes and what happens to it. If this is our A as a function of time, and this is our time, let us look at the various limits of this. When t is equal to 0, exponential is equal to 1. This one cancels that one, and so we begin at concentration 0. We start here. Then imagine that we've only just got the time going, then this exponential of a very small number, so when the time is still small, e minus x for a very small x, as you know, is approximately equal to 1 minus x. Those who did Taylor series in 1047 know exactly why. Those who didn't do Taylor series must have seen approximations like that at school. For very small argument, you can sometimes do that. And so for very small t, in other words, in the initial regime of that reactor, what we will have is A of t is approximately equal to K2 minus K1, 1 minus 1 plus K1 t. These two ones disappear. The K1s cancel, and so you are left with K2t. Therefore, when we've only just started the process, the concentration of our substance goes linearly, and it goes linearly at exactly the rate at which we are adding it. So the amount is increasing at the rate at which it's being added. That's simply because the actual reaction hasn't yet kicked in. And you have to accumulate a sufficient quantity of the reaction to start. And so it begins linearly, and the slope of that curve is exactly K2. Let us now look at a situation where the time is not small, but is instead very large. So for long t, we will have a situation where this t is very large. We have the exponential of a large negative number, which is 1 over the exponential of a large number, which is basically 0. So what we will have is this exponential would simply disappear for a very large value of t, and so we will have A of t approximately equal to K2 over K1. And you can see this makes a lot of physical sense, because the more reagent we add per unit time, the greater will be this steady state concentration. So if we increase K2, the steady state concentration is increasing. However, if we increase the rate of consumption, K1, then it will decrease. But what is important is what's called the asymptotic concentration of the substance is a constant. So there is a value here, K2 over K1, to which this curve must tend as time goes to 0. It's called an asymptote. So the long-term behavior is for the reactor to stabilize. And this is when the amount that we are adding per unit time is exactly equal to the amount that the reactor is consuming per unit time. And that is what happens if we are starting from a zero concentration. Now notice, however, that this asymptotic limit is actually independent of the value of d. So no matter what the value of this indeterminate constant is, the limit of this expression for very large t always has this term vanished. It goes to 0 when t is large. So actually the asymptotic behavior of the magnetization, the steady state of our reactor, is independent of the initial concentration of the substance and is always K2 over K1. In other words, if we start from other concentrations, so if there was something in the reactor beforehand, for example here, we will still have exponential return to the steady state regime. Even if we have the concentration in the reactor that actually exceeds the steady state, so if we start somewhere here, it will still return to the steady state concentration. So in these cases, it will rise until it reaches the steady state. In this case, it will fall until it reaches the steady state. And this is a situation that is known in mathematics. I'm simplifying rather a lot in here, but this is a stable physical system. If you perturb the system from this chemical equilibrium, if you perturb it upwards, it returns back. If you perturb it downwards, it returns back. So it will always stabilize itself and reach the steady state. There are situations in mathematics, and we will be dealing with them in, I think, 2 lectures from now, which are unstable. So they do have these things where derivatives are formally 0, but once you perturb it even a little bit, the system goes haywire, either in the positive or in the negative direction. Each other situation is. Finally, what we need to observe in here is that this asymptote that we have obtained dynamically is in fact also encoded in our artificial differential equation over there. If you remember the definition of the steady state, that is the situation where the concentration no longer changes. When the concentration no longer changes, derivative is 0, and so we must have minus K1 A of t plus K2 equal to 0, right? That's a steady state, and therefore A of t is actually also K2 over K1, exactly as we have here. So this can be obtained from the steady state. This can in fact be obtained from chemical thermodynamics. Remember reaction products and the reaction constants and the equilibrium constants. That's actually the equilibrium constant of this reaction. But it also matches the long-term limit cost full-time dependent ordinary differential equations in this system. Okay, so let me summarize the whole thing. This is somewhat deeper than what we have seen so far in chemical kinetics, because the people in chemical kinetics did not give you the inhomogeneous cases, because they have to also provide for the people who didn't have the mathematics A levels, who are rather terrified of this. But in this course, we will be looking at first ordinary differential equations and then partial ones. And you already know how to solve single homogeneous ones, and the way you solve the inhomogeneous ones is by a sleight of hand, like this, where you are looking for an undetermined coefficient. That's actually the name of the method. And after a great deal of mathematics, you arrive at a viable model for a reactor where the substance is being continually added or removed from it. It will be removed if our K2 is negative, but there are all sorts of things, all sorts of problems that crop up, because you would have a negative equilibrium concentration and so on. So something might suggest you that that model might not be a good idea. It will be unstable and it will be unphysical, but the model in which we are adding the reactant continuously is actually quite well behaved. And as you can see, multiple limits and multiple considerations from various perspectives on all produce exactly the same answer.